All right, so I know I need to collect a couple more reflections, so if you want to finish up some details as you're doing that. Just like as we're getting into the last couple weeks, because literally we have a little over a week to finish learning for this class, and then we'll be into exams, right? So we have to finish this unit, and then I'm going to do a half unit, not really going to do the last unit and a half that I usually like to do. Yes, sir? Say again? Is that supposed to be the normal distribution? Mm-hmm. Yep. Okay. And the empirical rule. But listen, at least I hope one of the things that y'all have gotten out of class, just thinking about it, is one, even if it's a struggle for you, I hope that you at least know that I care about you, and that's why I push you and I want the best for you. So think about that. And I also want you to understand, and I just want to make sure I verbalize this before the end of the class, if I didn't care about you and I didn't think you were capable, then I wouldn't challenge you to learn it. But I really wish Mason was as funny as he thought he was. So, if I did not care about you, then I would let you not learn anything. But I care about you too much to let you get out of a class without learning something. You're intelligent human beings. You're worthy of a class that actually gets you to learn something, and you're capable of a class that actually gets you to learn something. You still have a couple weeks to develop mastery with certain content. We still have a couple weeks to finish learning how to solve quadratic equations. We still have a couple weeks to learn how to graph lines. I'm going to embed that within the last couple of days of this unit. The next unit, when we go into something called a logarithm, we're going to bring back the exponential function. You've still got a couple weeks to master the ideas of an exponential and understand a logarithm. You've got advisory every single day to ask questions and get to master these ideas. Don't sell yourself short. Even if it was a struggle before, that doesn't mean you haven't developed those ideas better moving forward. And I got the note of one thing you want Mr. Kenny to know is most of us don't do any studying or do anything. Yes, I'm aware that's the problem. I need y'all to hear me clearly on this. In the most loving way, speaking the truth to you, you're not bad at math. If you have that mindset of, well, Mr. Kenny, I can't because I'm bad at math, you don't know, at least from my class, if you're bad at math, because if you're not doing the work, that's not being bad at math, that's being bad at being a student. But that's something you can easily change. Being a good student takes hard work and just effort and practice. That's something we can turn around in the last couple weeks. And I promise you, and I probably should have said this earlier, I was talking with Caleb Kelly, who just walked across the stage yesterday. He was in Advanced Algebra 2, and quite a few of his friends did not like my class very much. And like parents were coming up, were like trying to talk trash or whatever, and they came up to him one time and they said, yeah, and so what do you have in his class? And he was like, I have an A. And they're like, what? How? And he was like, I do the things Mr. Kenny asked us to do. He said, I knew that early on, within the first 3 or 4 weeks, that I could get frustrated or I could sell out and do the things you were asking me to do. And as soon as I decided to buy in and do the things you asked me to do, both inside the classroom and outside the classroom, it was easy. Like, I'm here to help you be the best person you can be. I'm here to help give you chance after chance after chance to master. Because I know you're capable of it. Doesn't matter where we start, it matters where we end. You got 2 weeks, and I should have said this before, but it's time for you to sell out if you haven't yet. Buy in, dig deep for 2 weeks, master it. Because I'm here to help you do that. Okay? So, let's get it going from here. We're going to finish up that lesson 3 from Carnegie Learning and then get into lesson 4 to help us, again, practice writing polynomials from the roots, identify polynomials from tables. Jordan, you want to grab a seat with the kings? Identify polynomials from tables, and then we're going to tie it all together. And so we're going to go back to understanding what a linear is today. We're going to go back to understanding what a quadratic is, and some other details like that. Thank you, thank you, thank you, and thank you. All right, so we're going to continue mastering those ideas. Please note, Bree was asking about it earlier. She was asking, hey, don't we have a test today? Which, by the way, a DYU is not a test. A DYU is to help you learn what you still need to learn before the test. Help me figure out what I need to address before the test. But you have DYU Monday is what I moved it to, test on Tuesday. Okay, we got to finish up this unit so I can teach logarithms. If I don't teach logarithms as an Algebra 2 teacher, I have failed. Which I won't get as much logarithms in as I wanted. I won't get any of the inverse unit that I usually do, but it's okay. So really quickly, we're going to finish working with what right now? Sketching, no, what was it? Is it in this one? It must have been the other one. We're going to be working on writing the equation of a polynomial when given roots. So that must have been the previous proficiency scale, and I forgot to put it in here. So one thing to help us build, I did actually put some of this in here, that's what it was. We're going to do a couple of these problems where we're practicing creating the graph and then writing a standard form equation from there, because I think a couple of us still need practice with that. Remember, you're in a small group for a reason. I cannot be everywhere all at once, but you all have somebody you can talk with, right? You all have support system, and if you are stuck in your whole group and nobody knows what's going on, what can you do? Before that, with whom? But what if your whole group is stuck? Yeah, look at your peers. Like, we got 4 groups in here, right? We got 4 people, or 4 groups to go around and talk with and make sense out of ideas with. And so don't forget, you have that resource here. You have that ability. Yes, if I'm over there, ask me those questions, right? If you're in a small group and your small group's rocking and rolling, ask your group those questions, because they are going to help you. And if it still doesn't make sense when you're asking your small group, then ask me for sure when I get over there, or go look at another group. I don't care when you learn, I don't care how you learn, I care that you learn, okay? So let's master this, let's talk through these ideas, make sure that you can explain what this crap right here means. And it's not actual crap, like this fun stuff. It's simple once you start to understand what's being said. But it does require understanding what's being said. Don't forget, I think it was somewhere in here on Wednesday made the comment, like, it's just this vocabulary that's tripping me up. Well, the way that you get better at the vocabulary is you quit saying the word it and you start using the vocabulary in its proper context and helping each other. Practice talking about these things. I think I mentioned that when you start to learn vocabulary, you don't memorize the definition for a ball. You play with the ball. You experience the ball. You throw the ball with your friends, your parents. When you start learning what chicken is, no one gave you the definition of chicken. You started eating chicken and talking about it with your parents. You want to learn math, you got to talk about it as you're experiencing it. Use the language of mathematics, use your proficiency scales, talk about it, ask about it, make sure you understand the vocabulary. You're capable of amazing things. Let's get up, let's work on D and E for the next, let's say 7 or 8 minutes, and then we'll have a what's called a consolidation piece where we wrap it up. So get out the pages 242, D and E, and that's where we're going to start today. Well, yes, but x-intercepts and what was happening over here with this graph that was not 100% correct at the beginning. Right here, difference between x-intercepts and x-intercepts and x-intercepts and she had the right number of, starts with an R, roots. She had the right number of x-intercepts. No. Guys, we got to remember the difference between x-intercepts and roots. Whatever the degree is, that's the maximum number of x-intercepts, but could it have less? 100%. Yes. You have double roots, triple roots, you have imaginary zeros. But this asked for 4 x-intercepts. We got to have at least 4 x-intercepts. And I didn't show it in my graph that I created in blue there, but could I have had some imaginary roots? Some funky stuff happening? 100%, right? So pay attention to those details, please. So when you write that equation, it's got to have an f of x equals or a y equals to make it a function, mapping those inputs, those outputs. Be careful with our 4 x-intercepts versus 4 roots. And then on this last one again, we need to make sure we clearly understand if it has 3 x-intercepts, It's gotta have at least a third degree that contradicts a second degree, as it says in the last characteristic. With equation A here, well, first off, what did we kind of like focus on and notice for our equations when we were given these zeros like this? What was this similar to? What have we learned that connects to the idea of a zero? Say it louder.
A root.
A root. What form have we looked at that deals very heavily with roots?
Factored.
Factored form, right? What was that factored form of a quadratic?
A parentheses x minus r1 parentheses x minus r2.
Bree, what did we mean by R1 and R2? Those are the what? Not the x-intercepts. We can get the x-intercepts from it, but
First root and second root.
R1, root 1, and root 2. Remember, the roots can give us x-intercepts, but remember right here, if I have these zeros or these roots, are they going to be x-intercepts? No, so remember there's a slight difference between a root and an x-intercept, okay? So here's the thing though, how many roots do we have?
3.
3, so it's not just going to be R1 and R2, we got to do R1, R2, and R3. And so, notice, all I'm doing is subtracting my 3 roots. We should have gotten there on Wednesday. I will point out, I left an A here. I'm going to explain why later. Tyler, I think you were the one who came up to me after class on Wednesday and we talked about how to get that A, right? With one of the later ones. Oh my gosh, right? Someone in school actually wanted to learn? Holy crap, the villainy of that person.
You going to bed?
We literally got this down on Wednesday. We did this already. Oh, we didn't write the notes that Mr. Kinney told us to write, and now he's going too fast because I didn't do the thing I was supposed to do the first time. Oh my gosh. Mr. Kinney's the villain now.
Oh my.
Okay? Now, what I want you to do in your small groups, this should take, and that's where we ended. Notice all I did was I subtracted my roots. By the way, I will point out, what is x minus 0 the same as? It's just x, right? So I'm going to rewrite that as just x. It makes my life a little bit easier. But what I want us to do right now, so we're going to later come back and we're going to rewrite this in standard form to help you get some practice with that. But what I want you to do is I want you to work with your small groups to write C and D in what form, since we have the zeros or the roots?
Standard.
No.
Vertex.
We have, say again, Bree? Say again? Factored form, because we have the roots.
Factored form.
Not C and D. All you have in C and D are the zeros. You know this weird thing called listening? It would be helpful if you tried it sometime.
I was looking at the other side.
Hey, okay. So C and D, let's get up to our vertical surfaces. Let's write those equations in factored form. By the way, you can't have a vertex form with these because you only have a, alright? So with C, we're starting to remember, right? If it's x equals positive 6, then it has to be x minus 6. And if it's x equals negative 5, then it needs to be
Plus 5.
x plus 5, right?
So could you have squared the x minus 6?
Adrian, is that what you did? So remember, it's a multiplicity of 2, so could I just put a square there?
Mm-hmm.
Is that an option? What does it mean to square something? It means to multiply it by,
2.
well, itself, not by 2. So, for those who wrote these two, are those equivalent ideas?
Yeah.
Yes. Now, I've talked about this with a couple of groups so far. Really, how many different A's are available? How many different things can we put for A? Infinitely many, right? And heck, I could have even done a 3 here as long as I made this an 18, because notice 6 would still be my root.
Oh, true.
Right? Or 6 would still be my 0. I'm not saying to do this, I'm just pointing out If I multiply this by 3 and I multiply this by 3, I still get a root or a 0 of 6. And so it's important to recognize there's infinitely many options, as long as we have the right zeros and we correspondingly change everything. Now we get down to D though, and we all got the x minus 2, the x minus 3, and the x minus 1. And I think there's some of us who weren't sure what to do with that y-intercept. Okay, is that fair? I want you to think about something, Mason. So this group over here, all right, they wrote, and we have seen this kind of work out sometimes, that whatever we're subtracting at the end is the y-intercept. But what do we know about every y-intercept that's ever existed? The x is 0, right? So if I substitute 0 in for x, what should I get out?
0.
I should get out a negative 24. Let's check it. What is 0 minus 2?
0.
2?
Nope. Negative 2, thank you. What's 0 minus 3?
Negative 3.
And what's 0 minus 1?
Negative 1.
So, that would give me 6a minus 24. Tell me, did I get an output of negative 24?
No.
I got 6a minus 24. But this does inform what we should do. So good thinking, I like that. But notice, and I want y'all to remember, putting that minus 24 at the ends like y'all did is connecting back to what form of a, it's connecting back to a standard form, but what form do we have? A factored, right? So we can't combine those two ideas. They are different forms. But what did we just discuss? That input of 0 should give us an output of what?
Y.
But what y? The input of 0 should give me an output of negative 24. So if I put 0 in for x, what should g of x become?
0. G is 0.
Remember, g of 0 is negative 24. So if x is 0, what's g of x? Someone said it already. Negative 24. As long as my x is 0. So notice whenever if I substitute 0 in, I should be able to get an output of negative 24. So notice, I want you to look at this. How many unknowns do we have? In that equation, how many things are unknown?
Just one thing.
One thing. What's that one thing?
A.
Yeah, I don't know what A is. But if there's only one thing that's unknown, can I solve for that A?
Possibly.
Not possibly.
Yes.
Yes. If there's only one unknown, I can solve for it. I need to simplify. So remember, to solve, what do we do first? Simplify. Then use your inverses with properties of equality. Now, I will remind you, that's not what you can always do, but if you only see your variable one time, you can use inverses with properties of equality. And how many times do we see that A?
Once.
Uno! So I can use that strategy. And we already did this earlier. What was it, negative 6? So what's happening between the A and the negative 6? And what undoes that multiplication? Division. So negative 6 divided by negative 6 is 1. And what's negative 24 divided by negative 6?
Don't ask me.
Positive 4.
Thank you. You also have calculators.
Forgot to grab one.
So A is 4.
So A is 4. So in this case, when they gave us an extra point, were there infinitely many equations? No. Let me say that one more time. When they give you an extra point, there's no longer infinitely many equations. Okay? So when they give you an extra point, there's no longer infinitely many equations. You need to substitute your input and output in respectively and solve for your A. So remember, that A could be anything. And these are the things I need you to make a note of. That A could have been anything until you got an extra point. When you get that extra point, it forces the graph to go through that point, and there's only one equation. Let me say that one more time for the people in the back who aren't writing this stuff down. As soon as you got that extra point, there were no longer how many equations? There were no longer infinitely many. There was only one. Substitute your input and your output in respectively and solve that equation. So substitute that input and output in respectively.
Yes.
Okay, we have got to keep going. So, here's what I want us to do at this point. Here's what I want us to do. Please listen. I want us to convert this to standard form. Okay? I'm only going to do two because we got to get moving. So, here's the ones I want you to convert to standard form. I want you to convert D to standard form first, and then I want you to do B second. Okay? Now, for your sake, Tyler, because we're listening, and Mason, we're listening, for your sake, let's let A be 1 here. Okay? So, convert this G of X from D first to standard form, then B here to standard form. Okay? So let's get up, let's get going. I intentionally picked those two. Let's work on converting those to standard form. I'm going to annotate one of the group's work, and so I'm going to look over here. Jordan, if you don't want to get in the camera, then actually I don't have you in it. You're good. All right. So I just want everybody to walk over here. Tyler, I need you over here so that you can learn from something. So there's two things I want to show, and I've already shown this to a couple of groups. Tyler and Mason, not even looking this way. Thank you. Jaden, Kayla, Samija, Adriana, Maipa, who of you to walk this way?
Have issues.
Got issues? That's not ideal. I hear you.
No,
I know. I got you. Mason, keep walking. Thank you. Because y'all started out great. You got sidetracked to the end. That's why I'm having this conversation. Not just you, but everybody. All right. So here's what I need us to remember, and this is a couple of things I'm going to point out here. So good job on using that area model to go to standard form. X minus 2 times x minus 3. Be careful with your signs. But what I want to point out is this. This group did what a lot of us did, where we just took that and wrote it into the next area model. But what I want to encourage you to do is to recognize what you have done is rewrite this right here, correct? Okay? So what you now have is this. Now that makes it more clear, especially if you had more factors after this, then I'm going to multiply these together. This is a clear progression of your work. And so we get down to here. Be careful with your positives and negatives. But notice what I've done is rewrite this, and what is still out in front? The 4. Notice that 4 is not being substituted in for x because that's not what we're doing here. What do I need to do with that 4 since it's out in front? I need to, what kind of multiply?
Multiply everything inside of the
Yeah, what's that called, Bree? I heard you.
distribute.
I'm going to distribute it. This is your standard form. You had to distribute it. Okay? You had to distribute it. That was it. Notice though, if you keep just bringing the equation down to the next step, it makes it more clear that you need to distribute each time. That's what we're doing to convert to standard form. Remember I told you that before. What's that area model really helping us do? It's helping us distribute, right? Convert to standard form by distributing. So notice we needed to keep distributing. So I'm going to give you a chance to write that down, those notes down in a second. I need to cover one more thing today. We have a PhD candidate from UA coming in, and so I'm going to she just needs you to do a quick survey, which is why I need your iPads charged. But I want to talk about this one first, so we're going to do this together for the sake of time. So x minus 0 is x, hey, right here, x minus 2i times x plus 2i. Really quickly, I do want to point out, does anyone know, oh, there's Mr. Drake.
Do we gotta get iPad?
Not quite yet. Hey,
Oh, fine.
thank you. Okay, really quickly, answer ourselves. Adriana and Mason, because I'm sure you started it, because I know who you are. X minus 2i times x plus, x minus 2i times x plus 2i times x. Which of those factors should I multiply first? I will say this. You can do any of the factors first. The easiest of the ones to use, though, are these two, because they are so similar. There's a special name for them called a conjugate pair. And so it will make it easier on you to do this. Now, notice, what is x times x? X squared. X times negative 2i.
Negative 2i.
Negative 2i x. Positive 2i times x.
2i.
Or plus 2ix. Notice, this is why I said this would be the easiest place to start. When I am adding something and then subtracting that same thing, what do I get?
0.
I get a 0. That's why I would do those two first, okay? Now, this is the most important part that I need you to pay attention to. What is a positive 2i times a negative 2i?
0.
Multiplying them.
Negative 4i squared.
Negative 4i squared. And so, I'm going to bring this over here. I need us to pay attention to this. You should not leave this factor this way. What's wrong here? What do I need to rewrite? Anyone remember what I squared is?
Negative.
Remember, the whole point of I is we defined I such that when it was squared, it was negative 1. Remember, that's why I is the square root of negative 1. So we should never leave an I squared. Really what we should be looking at is minus 4 times negative 1. But what do you get when you do a negative times a negative? A positive. So we should have x times x squared plus 4. Okay? And then you would distribute again. Remember, bringing it down each time helps you see when you can distribute. Notice, I don't need the area model, because how many terms are right here?
1.
So I can just distribute that one term. Sorry for that being a little bit faster. I still got to cover one more thing, and then, Mr. Rick, we still have 15 minutes till we leave, but we should still be able to finish before early on into advisory. So I promise I won't take up much of your advisory time. I'll give you a little extra time on Monday. So, x cubed plus 4x. Please again remember, do not leave I squared. What is I squared? It's negative 1. So rewrite that I squared as negative 1. That's the whole point of I squared, is now we can square a number and get a negative. Totally forgot to film this part, for the YouTube video. Tyler, can you go ahead and erase that since you're not writing anything down right now? So don't forget, Kayla, when you get I squared, how are you going to rewrite that? If you get I squared, how are you going to rewrite that? We got to know this. I squared is equal to what? Taj, you want to help her out? And then Kayla, I'm coming back to you. Taj, what do you get when you square I? How are you going to rewrite it? I squared is what, Kayla? So Kayla, what are you going to rewrite I squared as? -1. Do not forget that, guys. When you get that I squared, don't leave it as I squared. The whole point of that is it's -1. Alright. I need to quickly look at a couple of things. Alright? And I need to talk about something.
Oh.
Function type. If you have a linear, what's the equation of a linear? Or what's the degree, I really should say?
1.
Degree is 1. And what was the rate of change? Not necessarily. What was the type of rate of change?
Slope.
That's the name of it.
Mx plus b.
That's the equation of a line.
Repeated.
It is repeated something.
Repeated addition.
Not just repeated. Constant additive rate of change. Okay? Then we learned about quadratics. What degree was a quadratic? It was second degree, right? Anyone remember what the rate of change for a quadratic was?
Constant multiplicative.
It's not a constant multiplicative. You're thinking of something else.
Multiplicative.
No, that was something else.
Non-plus.
It was not multiplicative at all.
Constant factor.
Nope. That's okay. You're going back to exponential. So, -2 squared is 4. -1 squared was 1. 0 squared was 0. 1 squared was 1. 2 squared is 4. Okay. So, what's happening to go from 4 to 1? Subtract 3. 1 to 0? Well, -1. 0 to 1.
Plus
1 to 4.
Plus 3.
See, this is why you can't just say repeated addition, because that is repeated addition, right?
1. There's also subtraction.
Ish, but remember subtraction is a type of addition. What's happening to go from -3 to -1? Plus 2. -1 to 1.
Plus.
Plus 2.
Plus 2. 0, then 1, right? 2. 1 to 3.
2.
What is this right here?
Linear.
Just the green. Just the green. What is that green? It's the same over and over again, so it is constant, and we are constantly what? Adding. So Jack, if we're constantly adding, what is that? That is
Linear.
linear. Constant addition is linear. So right here, what is this teal? It is repeated addition, but what type of repeated addition is it? If that's constant, this is constant additive gave us linear. So constant additive gives us, have I mentioned exponential once? So you just throw in a shot in the dark, just Hail Mary, like hopefully it hits. But what did we just say constant was? Constant additive gave us linear. So what's this teal? We got constant additive. The teal is linear. It's not random, guys. Math is a set of structures and patterns. Like, it doesn't break those patterns. It stays consistent. English is one of those things where there's a bunch of structures out there, and then, like, we whimsically change things. That's not how it works in math, okay? Hey, Jacayla, can you please not draw my expo out and get, like, a pencil or a pen? Or write on paper is just not a good time for it. Okay, so I appreciate the apology. Linear additive rate of change, okay? So I want us to now think about this, just logically. So, logically, not shots in the dark, okay? Cubic has what degree?
Third.
Third degree. Any idea what the rate of change would be?
Constant quadratic.
So it wouldn't be constant quadratic additive then, it would just be, because constant means it's the same, right? It would be what? Quadratic additive? So let's actually quickly check it. Once again, I know you think you're funny, you're just not as funny.
No,
As
I'm
you
like,
think?
I'm so serious.
Sure, sure.
I'm so
Okay.
serious on this.
Alright, so negative 3 cubed is negative 27, negative 8, 2 cubed is negative 8, negative 1, 0, 1, and 8, okay? This is plus 19, plus 7, plus 1, plus 1, plus 7. Is that constant additive yet?
No.
No. Okay, I'm going to keep it going then. Minus 12, minus 6, plus 0, plus 6. Is that constant additive yet?
No.
Nope. But then you go from negative 12 to negative 6 is plus 6, plus 6, plus 6. Ah, that's constant additive. So then this is, what?
Quadratic.
Not the purple. This is constant additive, so the purple is linear, right?
The next one.
And then the next one here in teal, what had a linear additive? A quadratic, so this teal right here is quadratic additive rate of change, right? Oh, we're starting to see a pattern there? Does it have anything to do with an exponential?
Nope.
Nope, because exponential has to do with multiplication. But what do all of these polynomials have in common? They're all additive. All polynomials have an additive rate of change. So just a Hail Mary, not literally, because there should be a clear pattern by this point. Quartic, what degree is that going to be? That's quintic. Yeah. Quartic is fourth degree, so what's the rate of change going to be?
Cubic additive.
Cubic additive rate of change. Guys, these are patterns and relationships that are beautiful, they're fun, they don't change, they're awesome. Okay, so learn those things. I will wrap up before 9:20. So, I need us to pay attention to this detail right here, okay? This is just direct instruction. We will practice with this on Monday before you demonstrate your understanding and before we have a test or anything like that. So right here, h of x, I just want us to think logically here. To go from 32 to 5 is minus 27. 5 to 0, minus 5. 0 to 5 is plus 5. 5 to 32, plus 27, plus 85. I want you to notice, doing it this way, there's a lot of places to make mistakes, aren't there?
Oh, yeah.
Oh yeah, okay. One, we got calculators, so don't make those mistakes. Two, I'm going to show you an easier way in a second. So plus 22, plus 10, plus 22, plus 58. Okay? Have I gotten to a constant additive yet?
No.
Nope. That's a bummer. Alright, let's keep it going. Minus 12, plus 12, plus 36.
No.
Still haven't gotten to a constant additive yet, have I?
Close.
But, plus 24, plus 24. Haha! I've got constant additive. Let's go. So what had a constant additive rate of change, eh? Linear. So this in green is linear and additive. And what had a linear additive rate of change? A quadratic. So this in teal is a quadratic additive. And what had a quadratic additive rate of change?
Cubic.
A cubic. So this rate of change right here is a cubic additive rate of change. So what type of function was h of x?
Quartic.
This is quartic. Notice we just keep adding 1 to the degree each time until we get to our function. If you ever get a chance to go take calculus, it's not as scary as some people make it, but you'll learn more about why that holds true. This is one of the foundational elements to what is called a derivative, the rate of change, specifically with a polynomial. You'll study it heavily there. But I do want to make your life easy. or easier, okay? Watch this. Last thing. I lied on 920, I'm sorry. h of x, see how I was multiplying f of x and g of x? Yeah? So let's look at f of x really quickly. Minus 3, minus 1, plus 1, plus 3, plus 5. See, there's a whole lot less going on here, right? But these are my factors. That's constant additive. So what's this purple here?
Quadratic.
Well, the purple is linear, right? Remember, add 1 to the power. So what type of function is f of x?
Quadratic.
Quadratic, okay? Right here, in g of x. Once again, I found my constant, didn't I?
Yeah.
See how these numbers are way nicer to deal with?
Yeah.
Okay. And so once again, I got constant here. So in purple, what do I have? Linear additive. So what type of function did I start with? What had a linear additive? Quadratic. And you're going to have to play with this some, guys. There are definitely some check your understanding questions on the Fourier models. So what happens when I take a quadratic and I multiply it by a quadratic? I get a quartic. Because remember, how many zeros does a quadratic have? 2. 2. How many? So I have 2 functions with 2 zeros for a total of 4 zeros, giving me a quartic. Okay, guys, this is one of those things that we don't have a ton of time, and I'll go ahead and say this. I am going to move this into the exceeds portion of the proficiency scale instead of the target, but this is something that's just cool. It's a pattern that holds, that continues forever and ever, and it can help you find other things in math. Okay? So I have recorded this. I'll leave this up so you can take a picture, but Mr. Drake, you need us, everyone besides Jordan. Jordan, I never got form back from you, but everyone else did, so everyone else can do it. You need to go get your iPad, yep. Everybody needs to get their iPad out, and Mr. Drake, you'll give instructions, right? At this point.
Yeah.
So you have almost 40 minutes. Yeah.